So we're going back to our electrophilic additions, but in particular to our oxidation reactions. I just want to make sure that you're aware or remember that my focus behind these is this kind of weird, what are those transition intermediates, and trying to acknowledge what are the combinations that set those up. Okay, so if our Lewis acid is a nucleophile, we're getting that 3-member transition state. If our leaving group is tiny, we're getting a 4+ member transition state. Okay, the primary focus for our oxidation reactions, good thing I color-coded so nicely, is going to be our leaving group is tiny. And again, this very, very weird kind of overlap, but it sort of works to help kind of compartmentalize these. Here's again all of those oxidation reactions, okay, all kind of summarized out. And one of the things that we're going to find super in common with nearly all of these is that they're going to form some kind of cyclic penta intermediate. Okay, so we're going to get some kind of weird 5-membered intermediate going on with these reactions. The epoxide, which if you notice that very carefully with our MCPBA, the piece that was out here, has been removed because that's not a penta, that would be a tri, okay, or a 3-membered ring, and that was one that I would argue was already discussed, so we're not going to stress about that one right now. So in each of these cases, what we are looking at is effectively a 3 atom reactive site. Okay, that 3 atom reactive site is what's driving that chemistry. Okay, in the first one over here, we're referencing as the metal because that could be osmium tetroxide. It can also be our permanganate. Okay, and you'll notice that yes, there are oxygens still hanging out on the outside, and I may be horribly drawing that Lewis structure, and ultimately I don't really care. But that's that basic kind of core structure. The ozone does the same thing. It has that same kind of characteristics where we have that 3-atom reaction. How is this going to end up working as far as our alkenes go? Well, let's advance and look at what an alkene would look like. Our alkene aligns those p orbitals, and so what ends up happening is our electrons will come out. Okay, that oxygen very quickly exceeds its octet. So what is its quote-unquote leaving group? Okay, well, the leaving group ends up being that pi bond. Well, the argument that I'm making here, which is, we can have discussions about how horribly bad it is later, that leaving group is a lone pair of electrons. Okay, or you can make the argument that that pair of electrons is going to the metal and we don't have a leaving group. So the leaving group is so tiny, it's infinitely small, it doesn't exist. Okay, because we're in that system, now we're going to start seeing these larger cyclic intermediates happen. And this is where the electrons from that neighboring oxygen are going to immediately come in to interact. Why the neighboring oxygen? It's probably hiding the metal, making it difficult for the metal to go through and react as a second site, and so the other oxygen interacts. The result is that we end up forming effectively a 5-membered either transition state or formally ring. And in fact, I think in all of these, they're actually formally forming a ring. The same thing happens with our ozone. Okay. Unfortunately, I drew it a little bit sideways because the electrons of our pi bond are actually going to come out and attack this oxygen, okay, because the other oxygen is formally negative. That causes the pi bond to break. The electrons from our negative oxygen come out and pair up, and again, we see that 5-membered ring start to form. Okay, so they're all following that same basic kind of patterning behind it. Right? If that's all going to happen on the same side, note that what happens with the end result is that you're going to end up with oxygens formed on the same side. When we go through and look at the ozone, all sorts of stuff starts flying because we just fully oxidize the bejesus out of the thing. Okay? And that kind of minimizes the need to stress about that cyclic intermediate because the cyclic intermediate isn't largely dictating that final product. Okay, but for the permanganate and the osmium tetroxide, the stereochemistry of that final product becomes really important to have nailed down, we won't see the trans OHs. They have to come in as a cis diol. So if we can remember that tiny aspect of our leaving group, or the non-existent leaving group, then we have a way to help us remember that process and ensure that we get it right. So there is another, of course. Diels-Alder is a bit of an odd reaction that some people consider should be part of first semester, because this is a conjugated diene. Because it is a conjugated diene, officially our competencies say conjugated pi systems that you're supposed to be evaluating, so they say Diels-Alder should show up. Maricopa is the only institution I have ever been at that thinks Diels-Alder should show up in first semester. Okay, so to that end, there is a separate video that I do quote-unquote make you watch as a play posit that discusses it. You can decide to pay attention to it or not. Okay, but what's happening here is we are reacting a pi bond with more pi bonds. So the electrons come out. We're now forming a similar system to what we've been doing. We don't have a leaving group, so it's still fitting in this same basic patterning of what we see with the osmium tetroxide and with the permanganate. No leaving group means we form this cyclic intermediate. Okay, in the case of the Diels-Alder, it's not an intermediate, it's a formal product. Okay, so that reaction also fits in this category. It's actually not technically oxidation, but we don't need to stress about that. I just want to make sure that you're aware of it. So where we're going to go is now move on to our Syn Dihydroxylation mechanism. Okay, it's a bit obnoxious of a title there, because number one, mechanism would imply that we're going to show curved arrows through all of this. We aren't. The other part is we're using big words with the definitions of what's happening here. Really what we're doing is an electrophilic addition. Okay? How do we know we're doing an electrophilic addition? Because we're starting with an alkene. The alkene is donating electrons to an electron acceptor, which by definition is an electrophile. Okay? So it is still an electrophilic addition. Why are we throwing in these words Syn dihydroxylation? Well, the syn is in reference to how that reaction occurs. Well, if we followed my patterning for what we've decided on the mechanism, that fits the category where the oxygens are going to end up on the same side of the old pi bond, which is technically a syn electrophilic addition. Okay, so that's where the syn term is coming from. The dihydroxylation is just a fancy way of saying I don't want to be super broad and classify everything as cars. I want to call it very specifically a Tesla Model 3. Why? Because I can. Okay, because we can provide that extra detail. And what they're referencing is that when we look at the final product, you'll notice that we have two dihydroxys, our alcohols. We have a dihydroxy. Okay, we call it the alation because we had to get those on there. The process of getting them on there was the reaction we're looking at. Okay, very dumb question down below because it's the exact same one as the mechanism shown above. So when we're looking at our osmium tetroxide, we've got the mechanism sort of written out. So let's go through and take a look at it. Okay, we have the alkene. The alkene, again, is our source of electrons. It goes through and attacks our electrophilic oxygen. That oxygen would now exceed its octet, so it has to break a bond and the electrons shuttle to the osmium. Okay, at this stage, we might go through and say, well, why don't we just end with the structure with the positive charge on our carbon, and then this whole honking thing, okay, out here, why don't we just stop right there? Okay, and the reasoning for why we don't stop there is that we have electrons on that oxygen that are so incredibly close to that carbocation that they link up almost instantly. Okay, the sheer proximity of that makes it almost impossible for that reaction to not happen simultaneously. Okay? So we don't split it into a second step, and it all happens at once. Okay? 2 species, not 3, so it's reasonable. The result of that is that we don't have time for something to come in and align to the other side of that carbocation. It all has to come in from the exact same side. We add to that this oxygen has no chance in hell of going all the way around to attack on the other side. And for those people wondering why, all you've got to do is try and build this molecule. And what you will find is that that's going to be exceptionally difficult to go through and do. As a 5-membered ring, that's pretty much just planar. You're not going to get the wedge in the dash. Okay? So, we end with what is known as the osmate ester. We'll address that name in just a second. The big details to note is that our oxygens are connected on the same side. Okay? Do they have to be wedges? No. They could be dashes. As long as they are both dashes, they are okay. Okay? Technically, they are both present. This is why we see the statement plus an enantiomer. Okay? Next part, addressing the osmate ester. What is an ester? The ester is a carbon double bonded to an oxygen, single bonded to an oxygen, which is then bonded out to a carbon. That's an ester. If we go through and look at this, we have the osmium, which is single bonded to an oxygen, single bonded to a carbon, and that osmium is double bonded to an oxygen. So it's fitting the exact same pattern for our ester, except instead of it being a carbon, it's an osmium. That's why we call it an osmate ester. Okay? That's why it's fitting that category. And here's where I say it's dumb to call this a mechanism, because now what happens? After several steps, i.e. a mechanism that's too complicated for us to discuss, we end with our final product. Okay? So we aren't really giving you a mechanism. All we're trying to get you to do is to recognize the initial stages of this reaction, okay? The initial mechanism to establish the Syn product. Once you have that established, your job is done. You don't really need any other part of the mechanism. Okay? Which is a bit obnoxious in my point of view, because I think we should always look at the mechanisms. However, I don't know this mechanism, so I can't really explain it to you either. The big deal to point out is, again, that you need to ensure that you end with the Syn dihydroxy, or di-OH. Okay, that's the big deal here. So you see osmium tetroxide, you need that Syn di-OH. Okay. The next part that comes in fun is how would we now, because this is now looking at a mechanism, how would we see this as a reaction? That's where what we've got is down below. And I'm not asking you to predict it because it's dumb. It's written above. Okay. So you could see it as the osmium tetroxide written over the arrow, and then you might see something written down here. Okay. You also might not. That peroxide, as is what's being noted up here, is how we would regenerate the osmium tetroxide. So we're trying to remake it. Why would we remake it? Well, so that it can do it again. So we don't have to add as much of this reagent into our reaction to get it to go through and do it. Osmium's not exactly cheap. Okay? So we could add peroxide to refresh the osmium tetroxide so that it could go through and run this reaction and get our Syn diols again. That said, I have very often seen nothing written there and you still being expected to do the Syn diol, which means you see osmium tetroxide, we don't stop at the osmate ester. Okay? What you need to do is to continue to the Syn diol. Okay? So make sure that if you see osmium tetroxide, you're going to the diol and you're attaching them on the same side. Okay? We don't have to use osmium tetroxide. We can use potassium permanganate, which is a little bit more readily available and it will do effectively the exact same thing. Okay, so our permanganate, if we were to look at a quote-unquote mechanism again, with the negative charge, there's our permanganate, and I think there's a double bond out there. The pi bond comes out, reacts, shuttles the electrons to the permanganate, and then our negative comes in and interacts. We form that same kind of osmate ester type structure, except this time it's going to be a manganate ester. That manganate ester gets cleaved off via the hydroxide, okay, and a mechanism that, again, we don't need to know the details of, and establishes the Syn diol, okay, and that's what we need to be focusing on. There are some big issues with this one that we need to address that stand out a little bit different from the osmium, okay. There are some big assumptions. Number one, it needs to be cold, it needs to be dilute, and the presence of hydroxide isn't super important, okay, but it is typically there. So we are looking for this cold dilute system. Some problems with that. Concentration is rarely, if ever, specified in a chemical expression, okay, in a reaction arrow, okay, but excessive concentrations are noted, okay. We could see excess, okay. If we see excess, this doesn't fit the pattern of it being dilute, and something else weird is going to happen, okay. So don't do it, okay. Leave it alone and see if you can come up with another reason for why this might be going on, or what could potentially go on. The other thing you could be looking for is that temperature, okay. It needs to be cold. If it's not cold, then again, it's going to do weird stuff. Leave it alone, okay? Or recognize that it's going to do something else, okay? We could go through and look at the mechanism. We already just did that, so don't stress about that. And then the very next thing that's going to pop up is a question. So we'll go ahead and take a look at that one. Okay, so ignore the mechanism part. Go ahead and predict our products here. Note the big challenge. This is now a triple bond, not a double bond. But as we said earlier, our double bonds are just as or similar in reactivity as our triple bonds. So go ahead and see what you can come up with. So because I didn't give myself enough space over on the far right, I'm going to move it to the far left. Okay. Hopefully what you would go through and do is recognize that we've got some interesting potential chemistries popping up here. Of course, that's why I would ask it. It helps if I actually include all the proper carbons. Okay, there are our rings. And let's say we just run the reaction once. So that means we leave one pi bond, and then we would add our alcohols to this. Of course, I drew horrible geometries there, okay, but the horrible geometries are going to become relevant in the next step. Okay, this should set off alarm bells for you right now. If it doesn't, that's okay, and hopefully the alarm bells will set off on the next one. We still have a pi bond, so with that pi bond, we could react this again and add on another set of OHs. Okay, again being added to the same side. Okay, this is now where more alarm bells should be going off. Okay, if they aren't yet, okay, I'm going to redraw something and see if this helps you out. Okay, that should look familiar to you. And then we also addressed it as this. Okay, those should be familiar because what we're looking at is a keto-enol tautomerization. When we have that alkene next to the alcohol, it's a keto-enol tautomer. Okay, we can go through and fully form the hydrate. The hydrate, just like the enol, will both go to form the keto form first, or primarily, which means the product that we've got drawn right now is not correct. It needs to go through and form the keto form, and we get the diketone. Okay, just kind of a neat little reaction to watch out for. The alkynes do very similar chemistry. We just have to remember that our alkynes with OHs, or the addition of OH, can really kind of mess with our overall reaction, and we got to watch out for that keto-enol tautomerization. Okay. So the next reaction is looking at oxidative cleavage. So here we don't have to stress about the stereochemistry, but we're introducing that we're oxidizing so much that it's actually going to cleave the structure open. So there's really two pieces to oxidative cleavage. Okay, the reagents for this, permanganate, and notice it's now concentrated. Okay, we could also do osmium tetroxide and then periodate. So periodate is a good cleavage agent, and then O3. Okay, the two most common ones are the permanganate and the ozone, the O3, but you will sometimes also see the periodate. It seems to be making a larger comeback, and I've been seeing it pop up a little bit more frequently in both online in tests and stuff like that. So just be kind of aware of that. I'm going to leave the IO4- for you to evaluate in the textbook. I'm not going to address it here, but the mechanism is very similar to what we're discussing. So let's look at our oxidative cleavage. So if we're looking at our overall reaction, what's happening is we are cleaving. So there's the cleavage part. We're cleaving that pi bond, and we are replacing that alkene with oxygens. So we've increased bonds to electronegative elements. That's why it's oxidative. Okay, and it's cleavage because we've broken the initial connection, including the sigma bond between those two carbons. Remember, alkynes are similar in activity as alkenes. It does the same reaction. This particular figure I have a bit of a problem with because, yes, it's going to do the cleavage, but because there's nothing to stop it, it's also going to replace and put in more oxygens. Okay? So with the alkynes, you very commonly get more oxidation happening than you would get with the alkenes. The alkenes can have that oxidation stopped, okay, as long as you have carbons out at those ends, okay, or you have other reaction conditions, and we'll address that. Okay, so the reagents can sometimes prevent a continued oxidation, but the structure itself with carbons there can prevent that oxidation. With the alkyne, there isn't an extra carbon on the one of those pi bonds, and so when we go through and do that cleavage, we have this kind of hanging part. These parts are now hanging and need to be filled with something. In the case of the alkene, they were filled with carbons. In the case of the alkyne, I've broken that bond away, so they end up getting replaced with oxygens. So the alkyne tends to do a lot more oxidation than the alkene for that reason. That bond needs to be filled. Okay, so let's go through and take a look at the permanganate first, because the permanganate is interesting and that we saw it react already. Permanganate gave us Syn diols, and so one of the things with the Syn diols is that we needed dilute, okay, and we needed cold. Okay, so those I would argue would be effectively problems or complications of the permanganate. For the Syn diol is we had to have those conditions. What happens when we don't have those conditions? Well, that now becomes our problem, which now becomes an advantage. Okay, permanganate is such a strong oxidizing agent that it is hard to stop the dihydroxylation. That's why we have to be cold, and we have to minimize the presence of the permanganate to get the dihydroxylation. Well, if it's hard to stop, then don't stop it. Okay, just let it run. Okay, to do that, we change the conditions. Instead of being dilute, we now up it to being concentrated, and we'll say hot. Hot is in quotes because 50 degrees Celsius might be, well, that's not that hot. Okay, well, it's not boiling water, but that's still going to be uncomfortable. Okay, so that is hot. Okay, so what happens through our general reaction? Well, our electrons, of course, I've got this aligned incorrectly, but we're just going to have to deal with it. Okay, our electrons are established that we can go through and form our manganate ester, okay, and now what can go through and happen, okay? Whoa, what the heck? That was a pretty big jump, okay? Why did that go through and jump? Well, if we have enough heat behind this, okay, what's going to happen? What's going to happen is an intramolecular elimination reaction. That permanganate is starting to get a bit irritated that these things are stealing all its electrons. So it can go through and shuttle electrons from that negative oxygen down into the permanganate. This will cause the electrons internally to shift around. Okay, so there's the formation of that pi bond. Since I'm attempting to color code, we'll go ahead and do it that way. Okay, and there's our blue oxygen in there. Our carbon, our purple carbon, has now exceeded its octet. So what can happen now is those electrons can shuttle over to here to make that pi bond. But now the oxygen has exceeded its octet, so now the manganese can steal electrons back. Okay? And what we now end up with is the manganese has now stolen its electrons back, it's changed its oxidation state, and thereby also changed the oxidation state of the carbons. And we end with this aldehyde in this particular case. Okay? What becomes interesting with permanganate is that it is an exceptionally strong oxidizing agent. And to oxidize, we need to have hydrogens. Okay? And if we go through and look at the carbons that are reactive now with those oxygens, there are still hydrogens there. Those hydrogens could be removed so we could decrease the hydrogens and we could increase the bonds to oxygen. The question becomes is how do we go through and do this? We have to have an explanation for it. Okay? So before we push that too far, let's go through and start to think about some of this. What is the reactivity of that new functional group? Okay, so this new functional group we will officially see in second semester, so you don't have to stress as much about it, but let's take a look at it. We have the aldehyde functional group. Well, the aldehyde is reactive because the oxygen is more electronegative than the carbon. The electrons get withdrawn upwards. We would form the negative oxygen and the positive carbon. If we use our first worst resonance, we actually understand some of the simple aspects or the quote-unquote obvious reactivities of the aldehyde, and this helps to explain the reaction. Okay, why does it help? Okay, well, I have a positive carbon that wants to be stabilized. Oh, wait. In the presence of enough heat and or strong base, that hydroxide can come in and attack. Okay, why does that become important? Well, what do we produce if the hydroxide comes in and attacks? Let's see if, we'll look at that in a second. Okay, we would produce a diol. What's special about the diol? Do you remember seeing this structure? Oh, the permanganate can re-coordinate back to the diol or re-react with the diol. Okay, once it does that, we now form that special intermediate. That intermediate, in the presence of acids, will go through and do a similar mechanism that we just evaluated, where we will go through, oops, sorry, I'm going to pause for a second. Yeah, there's the chink in the armor. I had to show you what I was doing, or had to think about it first. Remember that we still have that hydrogen there. Manganese is really wanting those electrons back. If the manganese steals those electrons back, that oxygen needs electrons from somewhere. It can steal them from the hydrogen. Okay, that hydrogen is now lost as H+, which is cool because it's not like we didn't have hydroxide floating around. That hydroxide can pick up that hydrogen, okay? But then the manganese stole those electrons. The other oxygen will steal electrons back. The end result of that, so not after these arrows, so ignore that for the moment, is that we get a negative charge on that oxygen, a double bond there, and I drew too many carbons, of course. I think I can fix it fast. and we'd have a carboxylate. Okay, that carboxylate can then react with the H plus in a second step. Notice that's a second step, number 2, okay, and fully protonate to get us the carboxylic acid. Okay, so what does that mean for us? So if we walk all the way back through this, okay, where we started with the permanganate was that cyclic alkene. And what's going to happen is we are going to oxidatively cleave that and replace that with oxygens. Because permanganate is such a strong oxidizing agent, it will continue to oxidize until we've replaced all of the hydrogens on our active carbons. So those active carbons are our parent alkenes. We aren't touching any of the other carbons, and we will oxidize those positions as fully as possible. So any place there's a hydrogen, we will replace with oxygen. Okay? The chemistry shown in the upper right-hand corner is some hidden chemistry that's second semester. There's our negative, there's our positive. The oxygen can come and connect. We get what's known as a hemiacetal. That hemiacetal can undergo an SN1 type mechanism, and it can form the full acetal. Relevance for that? Well, that's partly what's happening within this reaction. We're going through and converting that carbonyl to the hemiacetal or the hydrate. And partly I like showing that because that is in critical chemistry for second semester, because we're looking at the acetal for biochem in carbohydrates. Okay, so with that, we've got our basic patterns for our permanganate. So I'm going to give you some time to go through and practice. So again, hit pause, try and come up with some products for these, and then in a few seconds we'll see our answers pop up. And by a few seconds, I'm just going to draw in the first one. Okay, and you might be like, that's kind of a dumb one to show, Mike, because didn't you just tell me that this was the answer, that when I went through and did this, I ended with this structure. 1, 2, 3, 4, 5 carbons. Good that I ended with this structure. You're right. That is where I ended. Is that where the chemistry ends? Remember, there's still a hydrogen there, which means that can undergo another oxidation. We're going to end with another OH. Okay. The other reason why I talked through this one a little bit faster, or before I did the long pause here, is that we would typically not see it drawn like that in an answer choice, where almost undoubtedly 1, 2, 3, 4, 5. See our answer written like this, where it's pulled out into that straight chain. And to make matters extra fun, you would probably see answer choices along these lines, where the only difference is the number of carbons. Okay, so make sure you count your carbons correctly when you go through and evaluate, because 6 carbons didn't occur. Okay. Reaction conditions, I want to note for these, sometimes you'll see it as the hydroxide, sometimes you'll see it as H2SO4. Both end up working. If we run it as H2SO4, we don't need the second step of HCl. Okay, so with that, you've got another one that you can go through and practice on your own. So go ahead and draw that one out. Cool. Hopefully you were able to go through and draw out, whoops, as I attempt to do it, screw this, 5-membered ring. Okay, and then we could go through and bend that out a little bit, double bond oxygen, OH, and then double bond oxygen. Note that this one's a little bit different. Okay, this carbon didn't have that extra hydrogen to oxidize, so we end up not fully oxidizing, or we oxidize that one as full as we can, which means we stop at the ketone. We don't get to take it all the way to the carboxylic acid. Okay, The other oxygen had a hydrogen. Because of that hydrogen, we got to an extra oxygen. Okay. Again, if we were to look at an answer choice on this, 1, 2, 3, 4, 5, 6, you'll hear me counting these out, 2, 4, 6, to ensure that I have the number of carbons right. We've got our oxygen. I thought that was the blue pen. And then at the other end, OHO, and then I would count it again, 1, 2, 3, 4, 5, 6 carbons. We started with 6. All we're doing is adding oxygens. Okay. Last thing I want to do on this, before I give you yet more practice on this particular reagent, is, I didn't want to delete all that, is show a potential cheat to get you to that black and red answer faster. Realize that when we're looking at these, we've got our 5-membered rings. And so what I'm going to do is really stretch that last bond. Okay, and the reason I'm going to stretch that last bond is that when we're doing cleavage, we now need to break that bond open. So it is now broken open. In the process of breaking it open, I'm also going to introduce some oxygens. So there's an oxygen, there's an oxygen. I then also need to evaluate, does that have hydrogen? Yes, it does have hydrogen, because this is permanganate. Those hydrogens need to become OHs. And I now have my answer. So I have a pseudo cheat on this. You can stretch that pi bond, erase the middle out of it, replace the middle with oxygens, okay, and then evaluate, do you have those hydrogens? The same thing would work with the other one if we want to test that one real quickly. So we kind of stretch out the pi bond. It's easier if it's not a cyclic structure. The cyclic structure makes it harder to kind of fold back on itself. So we can erase the middle out of it, replace with our oxygens, and now evaluate, do we have hydrogens? Well, this one already has 4 bonds, no hydrogens, so I'm going to leave that one alone. The other one indeed does have a hydrogen, so I'm going to erase that hydrogen and I'm going to replace it with an OH, and there I have my answer again. Okay, so the oxidative cleavage does have a pretty nice cheat for moving through and trying to get that answer. Okay, to give you just a hair more practice with that, here's 2 more questions. Go through and see what you can come up with, and we will come back to the answers. So mostly worked out. Let's start with the first one. I only stretched one of those bonds. You'll notice that on our bottom structure, we have those 2 hydrogens, which means those 2 hydrogens need to be turned into OHs. This compound should look familiar because this is H2CO3. H2CO3 immediately becomes H2O and CO2. Okay, for those people being like, damn, how did you know that? You should know that because you should have learned that in Gen Chem. Okay, so you are responsible for knowing that, which means at the end of this reaction, if we were expected to specify products, these would be the products we would expect to get. Since it's OChem, we're probably only going to see this structure. We might see just the CO2. It's rare to see the H2O show up as an answer choice. On the far right, you might be like, well, dang, you stretched a whole lot more pi bonds than you did for than the left one. The left one, you didn't touch any of the pi bonds in that ring. And you're right, I didn't, because that is a benzene ring. The benzene ring pi bonds are very stable due to that internal resonance. When we look at the rightmost structure, there is no resonance, which means those pi bonds are independent of each other and do need to be reacted. So we could go through and do our cleavage again with a little bit of erasing, drop in our oxygens, acknowledge, do we have hydrogens off of those pieces? Indeed we do, which means we get to erase all of those hydrogens that I just drew in, and I get to replace them with OHs. Oh my goodness. Okay. triple bond, we go through, we erase the middle out of that, and we draw in our oxygens. It's hard to have that triple bond to an oxygen, so how do we fix it? Whoops. I'm going to fix it by off-centering it just a little bit on the 2 oxygens, and I'm going to rotate that last triple bond down to a new oxygen, and we get a new OH. Same deal on the other side. OH. There's a hydrogen out there, which means I'm going to turn it into an OH. I again am going to decompose into CO2 and H2O. Okay, so fun questions that can typically come out of this. How many products are formed in the following reaction? So let's take a look at the left one. How many products do we get? There's a lot of things drawn there. We went through and starred them. Okay. In that black circle, we would end up with 2 organic or carbon-containing products, and that's typically how the question is asked. We don't care about water as an inorganic material, so we'd say we get 2. For the right one, outside the box, how many products do we get? There's 1, there's 2, and there's 3. Okay, so when you're being asked how many products, you need to consider the reaction and recognize that you could be breaking the compound into multiple pieces, and that's where you're getting all those aspects. Okay, so with that, because again, we don't get time to just sit and play with practice, we encounter another oxidizing agent, and that's going to be our ozone. It is also a very powerful oxidizing agent, but it has more control than permanganate, okay? Which means I can follow up ozone with a second step. That second step is happening down here, and in that second step, depending on what species I put here, I can result in a non-oxidation. Okay? Why? We've got tons of oxygens. Why don't I get that oxidation? Well, let's take a look at that species that I circled here. We have what is known as DMS, dimethyl sulfide. What's the other product? Well, dimethyl sulf oxide. Okay, so we have dimethyl sulfoxide. If we add as a secondary reagent an atom that can scavenge oxygens, our organic compound won't fully oxidize. Okay, that's what's known as a reductive oxidation, which is an apparent contradiction in terms, but that's what's happening. Okay, or that's how we call it. So when we go through and look at our overall, you're doing the addition to the ozone of the pi bond. It does the cleavage, but now the question comes with our intermediate, as we've been drawing even for the ozone. Okay, are we under reductive conditions? If we're reductive conditions, we're done. If we're under oxidative conditions, we need to convert that H into an OH. And then we'd be done. Okay, and so this would be our oxidative conditions. How do we know? Not oxidation, oxidative. We know because we have to look at that secondary reagent. That's that step 2. That step 2, looking at that reagent. Okay. If that reagent has oxygens, guess what? It's oxidative. Okay. If you don't see oxygens, then it's reductive. That's going to be your easiest way to differentiate that. Okay. So DMS, or dimethyl sulfide, is kind of your default reductive conditions. Your default oxidative is H2O2, but you can also get away with it sometimes, I've seen, as just plain water. Okay, you are supplying that oxygen, that gets that oxidative condition happening. Okay, so we just need to be aware of that when we go through and run the reactions with our ozone, is that ozone has that secondary reagent functionality. I sure hope you guys can't hear what's going on in there. That's just goofy. So with that, we've ended our oxidation video. This is long enough, so I'm not going to tag the the reduction in on top of it. So good job. And actually, I'm going to pause the video real quickly. We've covered all of our oxidative except for the MCPBA one, because that was a different reaction. So we've covered our osmium tetroxide and our permanganate, okay, which were effectively the same reaction. Okay, and then we've covered our permanganate and oxidative ozone, and then we have our reductive ozone as well. Okay, so those were our primary categories that we had within this. Lots of chemistry. We really only covered 5 reactions. We spent 10 minutes per freaking reaction, sort of. And so with that, I'm going to go ahead and end this one. Good work. Keep practicing. It's really going to come with the practice behind this. That's how it's going to help you remember these reagents.